Welcome to today's training. Today we're going to be doing a model for 2D liquefaction analysis of a bridge abutment. My name is Francisco Martinez and I'm an engineer at MIDAS. So this is a follow-up to the series that we started last week where we had a case study over liquefaction. Today will be more on the how to set up this kind of analysis on MIDAS itself. So just to recap what we saw last week, as we know, the soil liquefaction happens when either through rapid loading or some sort of earthquake shaking, the soil or sand that's saturated loses its strength and its ability to basically support any weight. So all the pressure generated forces the liquid to the surface, all the excess pore pressure rises to the surface, and then it basically becomes almost like a quicksand behavior. And at that point, either bridges or large buildings with pile foundations lose their support and eventually end up either tilting over or resettling in a way that was not intended. And this also happens for what would be embankments or what would be sloppy ground next to rivers or lakes. And so there are different methods for having studying these kind of phenomena. Typically for 2D, we have two main options. One would be the pseudostatic approach, most common, a limit equilibrium analysis, limit equilibrium method analysis of some sort of embankment. And for that, we have programs like well-known programs like Slide. MIDAS actually has its a 2D conventional method software called SoilWorks that can also handle these kind of pseudostatic analysis. But for more advanced, we do have other approaches, other options, which would be numerically based analysis. As we saw last week, we have either finite element method, which includes MIDAS GTS NX, but there are other software like Plaxis, like QuakeW, or notoriously the FLAC for finance difference method. So just a little more into these two options. For the static analysis method, we're simplifying. We're representing a very complex dynamic earthquake shaking in what would be a single unidirectional load. You basically apply some sort of seismic coefficient and you give it a direction, and that's the main thing you're analyzing is just getting the factor of safety. So for most software, or for this approach, you cannot get even results for deformation. You only get the factor of safety. And so this would be a very crude, basic approach. It serves well for its intended purpose, which is basically screening. But of course, it's not going to give you enough information. And when you end up getting here, we would see with MIDAS SoilWorks, and this would be for another program similar, I believe it's Slide, but in this case, we're actually looking at the same slope from last week's session, the same embankment that we saw for the AMA case, but in this case by pseudostatic analysis, by two different programs, and in both cases we get about a factor of safety of 1.5, which might be acceptable by some norms depending on the region. But of course, it's a big assumption that we don't know what's happening with the pore pressure. We don't know what's happening with the deformation of the embankment. All we have is a seismic coefficient giving us a general idea of what might happen under a static load. So of course, we have to luckily have other options, and we should be using more complete approaches, which would be by the numerical method. So in this case, it's either finite difference method on the left, which is this is what a typical example, or actually last week's example looks like, including how to, in this case, some of the code for generating the model. As we know for FLAC, we have to set up the model in some sort of loops encoding, which can be a little difficult. And then the alternative is to use finite element softwares like Plaxis or MIDAS, in which case we will show the procedure, but you will see that it's much more hands-on approach. The interface is CAD-based, so it's very easy to start even from scratch, to draw, to mesh, to everything. And also we'll see the extracting the results, especially the deformation results, and the important results also for liquefaction being the pore pressure and which layers have become or susceptible to liquefaction. So this will be the bridge abutment model that we will be working on today. As we see, we do have identified a layer for what would be the liquefaction layer, in which case we will be using a constitutive model, UBC SAND, for this. This will be a 2D analysis, and we're basically just going to start off by just opening a file. This will be included for download in our page, but you can also request it directly to us, and we can gladly share the start and final model for this training, as well as the video and the PDF. Here's a chart of the material layers that we'll be using. For all the other layers except for the structural components, we'll be using more column. And the nonlinear behavior by that is captured just basically by cohesion and friction parameters, whereas the liquefaction layer has some more specific advanced parameters that I'm going to go over just to clarify. And so it takes a little more calibration, of course. So a quick overview over this constitutive model. It was developed to simulate the liquefaction phenomenon. It's a plastic theory based on explicit method for 2D of effective stress state, and then it's extended by the implicit nonlinear method for 3D. So the elastic behavior is basically nonlinear elastic behavior captured by the modulus of elastic modulus. And then the plastic region, once it goes to that, the behavior can be defined by 3 yield functions: the shear hardening function, the compression or the cap hardening function, and the pressure cutoff. So we have three parameters we can use to define the plastic behavior. And so for the case of shear hardening, the soil densification can be taken into account by the cyclic loading. So if you were to look in our reference manuals, you can get the full constitutive model theory. I guess for now I will just leave these references as what was used for the original development, but we do have our manuals that will allow you to look at all the equations and the graphs in detail. Another important thing to point out, when we're defining the material for liquefaction, the UBC SAND, the main behavior will be captured in the nonlinear tab, but the porous tab also is important. We have to specify the undrained condition, that this would be an undrained material type. And from this, there's several options from which we can select. So in order to capture the excess pore pressure generated in the soils, we do need to be doing this analysis. The loading has to occur under undrained conditions. And for the analysis we'll be doing today, we will select the method or the choice effective stiffness, effective strength. This is the most general case for this kind of undrained analysis. And for that, there are 2 options for defining the behavior. So the standard value that we typically, or what we recommend for the Poisson, is basically just use the Poisson ration option at this value, at 0.495. And then the same material, but under the nonlinear tab. This is what the table would look like when you are defining the material. And these are what the parameters are. So the most important ones being, as we had seen, the elastic shear modulus number and its exponent. So as we had seen, this is what's going to capture the elastic behavior. And then the shear behavior The friction angle would be the same as in the Moore column. The cohesion value same as in the Moore column. And then these will be the ones that control the plastic shear modulus, principally the KGP, and then this is its exponent. And there's a few other parameters like the failure ratio, there's a recommended range of value. We have the post-liquefaction calibration factor. This is basically the residual shear modulus. And then we also have what would be the soil densification calibration factor for the cyclic behavior. And then a few of these advanced parameters. As we had said, the program gives you up to 3 options to capture the plastic behavior. So this would be where you define those. You would activate, these are optional, and you would activate these boxes here to give those values for the cap or the pressure cutoff options. So from here on out, I'm going to open the program itself and just go through this tutorial. As I mentioned, the materials and the geometry will already be in place, but I'll show where to expand this in case that you wanted to explore it, give it a second look, or in the future, if you were to define the materials initially, it would be the same steps, but I'll show exactly where that is. But for now, the materials and the properties, which would be for the soils, all 2D plane strain, except for the piles, which are beam, they will all be defined in the start file when you're trying this on your own. So let me just go ahead and start the program or open the model. So when you initialize the program in Midas, the first thing you'll see is it'll give you a choice between working in 3D, in 2D, or axisymmetric. So this, off the bat, pretty advantageous. In some programs, you are limited to a single version that you can work with. In our case, we have these 3 options. So we'll be working in 2D with the basically gravity in the y direction, and this is where you can set your units. I will change this to seconds since we're going to be working with a seismic function that is also in seconds. What we have here is then the interface of the program. As I mentioned, it's more of a CAD-based approach. There's no programming required, and it's not a drop-down menu like a Windows. You basically just navigate through tabs, and you see all the commands. If you hold your mouse over it, there's a bit of an explanation. At least on the name, expands the name a little bit. And there's a logical sequence, geometry, mesh, and then depending on the type of analysis you're doing, we group certain boundary conditions and loads together. So that would obviously for dynamic, like a ground acceleration has to be in this load type. And then you would do an analysis and then look at the results. So we'll go through this whole process. Also, something else to point out, we do have an online manual, which you can either press F1 as you see here, or just click on this question box. You would follow the third option, and what you can do is use this link to rib menu. You can still navigate it by doing a regular search or tabs, but if you do the link to rib menu, you can navigate the manual as if you were working or navigating the software. And so if you click on any of these commands now or loads, you would get the full explanation directly. So this is also quite handy when you're getting started. Just go into our online manual and you can navigate the interface as if you're navigating the program. So for here, I'm just going to open what would be the start file. As we see, we have the geometry already included. If I wanted to modify any kind of this is like a simple DXF file or DWG file that can be imported. But if I wanted to modify it, add new things to it, I can activate this grid, which would allow me then to draw directly on it any kind of new geometry. And so similar to AutoCAD, I would use different commands to either extrude or modify or translate or rotate. I can also change the side dimensions of this grid, activate the origin, or different views all from here. So these are more of the views menu, and these are more of the initial conditions for drawing in 2D. So in our case, we have the final geometry in place. And if I expand here the works tree under the model tab, we see that the materials are, you can verify the materials, they're already defined, as well as the properties. But if you wanted to define them from scratch, you would just go to the Mesh tab and you have both of them here. So just looking at these, as I mentioned, for the soil layers, there are more column. The structural components like the abutment and the pile are elastic, and our soil layer, or our liquefaction layer, will be UBC SAND. And these are the 3 tabs that I mentioned. These are the conditions for the porosity behavior, and then the nonlinear behavior, of course. So from here, we would just proceed to just start meshing. We've basically, let's say, imported the geometry or started already by finishing drawing our geometry and defining our materials. So you can proceed on to generating meshes. Here, all the materials have to be specified as to how they're going to be used. So of course, being a 2D model, all of our soil layers are going to be 2D. And then of course, we're going to have the piles, which is our 1D beam. And from here, you actually don't fill out these values yourself. You can just specify a section, which we have a pretty extensive, what would be database for different sections, including by code. And the program would automatically update these values. And here's where, if you're doing 2D, you can also specify the spacing. So for now, we're just doing what would be a pipe with the following dimensions for the pipe. So I'll just go ahead and start meshing. I'm going to select the area option. We don't have any faces at in terms of what the program is recognizing for selection, but we do have options for just area, which is then the filter has become edge, and I can directly click or draw rectangles to generate an enclosed. So long as my area is enclosed, then I will be able to mesh. So this would be embankment, and I can select this other end of it is also an embankment, as we have there. So I would just give it a name here. And just for reference, we do have this advanced option here, which you can select what kind of element you want to use, if you want it to be only triangular, quadrilateral, or mixed. If you want to use higher order elements in case of a slope stability analysis. In this case, I'm going to turn this off since I'm selecting multiple geometries, but I want them to be considered under the same set. Well, in this case, it didn't. I must have missed a section. So you can scroll in just to give it a zoom. We do have a preview button to see the size, and I will continue this process based on the map from the initial slide. So this is also an embankment layer. This would be my liquefaction layer. This would be my weathered rock layer. And this would be my soft rock. And lastly, the bridge abutment itself. So here in the workscreen now, if I expand the mesh tab, we have all of our sets. We see here, after I reopen the window and then mesh the abutment, I didn't specify to mesh them all together. But what I can do is I can just select multiple ones and drag and drop them into another set to merge them if I wanted to clean this up a little bit. Same for this embankment. So now we have the 2D meshing complete, and we can proceed on to mesh the piles. In this case, what I can do is either just mesh directly 1D or extract the element, which is also common practice if you're doing some sort of excavation model. And we can do it directly from selecting geometries, edges. So here in the workstream, what I can do to make this a little easier is just deactivate the things that have already been meshed and leave only the geometry so I can extract the piles easier. What I want to do is just try to select by drawing a very narrow rectangle. I only want the vertical lines for the piles. Okay, so this would just be piles. Here's where we've done the property. And in this case, because I meshed the soil layers while selecting also the inside lines, all the nodes automatically line up. I don't have to specify division, especially if we're using the extract command. Had I just done a regular 1D mesh, it would also not have mattered how many divisions I gave it, because the program already understands that there's nodes associated with those locations. And so it will match the connection automatically. However, what I do have to inspect real quick is the orientation for my 1D elements. So I'm only activating the piles, and I'm going to turn on here what would be the coordinate system. It seems here that most are matching except maybe for this one element, and all that would mean is then the results, the positive direction and the negative direction of, let's say, axial forces would mismatch. So I just have to correct that one or two sections really briefly. So for that, I can just go here to parameters, and we see we can modify different things for any 1D, 2D, 3D other. For 1D, I would just select to change the coordinate system. I'm going to select it all, and I'm just going to tell it to match one of the elements, in this case the one facing to the right. And now they're all matching. As long as they're all matching, it doesn't really matter. So I can turn that off. So now we will proceed to apply special boundary conditions for the first type of analysis that we're going to do, which is going to be an eigenvalue analysis. What we want to do is we want to get the main vibration periods, the main modes of vibration, and write down those periods so that we can use them later in the time history analysis as part of the damping process, the Rayleigh damping. So what we'll do here is we'll go to mesh, we'll go to create, because this is our special boundary condition element. And so this kind of element is grouped under other, and it's a ground surface spring. So we would just select the soil layers, these main soil layers that have boundaries. We don't select this one because it doesn't have a general boundary on the right side, so it won't need this kind of boundary condition. And so the program will calculate the modulus of subreaction automatically. We just give it a value for this coefficient, seismic coefficient. In the previous last week's session, as well as in the PDF that we will include for this training, we cover how the program uses the material properties as well as some of the dimensions of the element to calculate what would be a vertical and a horizontal modulus of subreaction. It creates individual spring constants for the different directions. And what we also want to activate is the fixed bottom condition. We want to create a fixed bottom boundary condition. So once we do that, we can kind of see a small, maybe if I deactivate and only activate that, you can see the elements that have been created along the boundaries, as well as if I now go to the analysis tab and turn off the other fixed boundary condition, there's also those elements at the bottom. And those, if we go now to properties, you can inspect one by one here under modify. But basically the program, based on local materials for each different layer, has created different spring stiffnesses in the different directions, as well as created this fixed boundary condition, which we can see here. So we would then proceed to create the analysis case. Well, what we would also need is just to activate self-weight, in this case, gravity, or if you needed to apply any other load. And then we would just go now to either Analysis tab, General, or the analysis case here and go to Add. It takes us to the same window. What we're going to do is create an eigenvalue, select from the menu. This is all the analysis or solution types we have. We're going to select eigenvalue. And just activate everything by clicking on this. In the analysis control, we can specify the water level that we want to consider. In this case, this is a global height, so we're just going to use the value of 2. That's based from the origin. We can select the number of modes we want to consider. And in this case, if we don't want to specify frequency range, we can just activate Sturm sequence check. And of course, we need to consider undrained material behavior for our UBC SAND layer. So from here, I would just run it. And what we'll see here is our output window, which will give us information about the process, how long it took to run, if there were any warnings. We see that for this kind of 2D model, it's very quick. And we can now go to the Postprocessor to see our results. So here you can individually see all the different modes of vibration by double-clicking. But what we really care about is this table here, the eigenvalue analysis result, which if you double-click opens details about all the different modes. And if you scroll down to the last box, you see here we would have what would be the mode mass participation by percentage. So we're going to be running an analysis with the seismic function in the x direction, which would be the T1, y direction would be T2. So we care about mode number 1, and the other one with the most participation would be node number 6. So we go back to the top of the box, and we would write down these periods or frequencies. In this case, I'll just do periods. So I'll write down that 0.409 and 0.190, or in those ranges. I would write it down in a box or somewhere. And those are the values that I'm going to be inputting later for my damping, my Rayleigh damping in the nonlinear history analysis. So you can take a screenshot, write it down, or whichever it is you need to do. But we would go back to the pre-processor mode in the model, which is here. And we would now prepare the model for what would be the seismic analysis. So that was just one of the steps that we needed for the time history analysis. But for the time history analysis, we're actually going to apply a new boundary condition, an absorbent boundary condition, which we call is a free field element. And we're going to apply it on each side of the model. And these elements are useful for 2D or 3D. So we would just draw a rectangle on each side, and specify to the model that we want it to be absorbent boundary type and give it a width factor. In this case, we recommend 1 to e to the 16th. It's a really high width factor. So I'm going to go to mode and the model tab in the worktree and deactivate the sets, or I could delete them. I don't need them anymore. For the surface springs, that was only for the eigenvalue analysis. And I'll go to the mesh tab, go to free field, and from here I would select or define in this box what type, if it's a free field or absorbent boundary, and the width factor that I want to use for my boundary condition. For the start file, the property already includes this free field, but just to show you where you would, if you wanted to define it, you could do it here. So I would just select both sides of the boundary, of the vertical boundaries, and click apply, and we see now these new elements. So these are the free field boundary elements. If we deactivate we can just clearly see they're only for the boundary. And we also need to now reapply a bottom boundary condition. So when we created the surface springs, ground surface springs, we just basically told the program to do this in the same step, and we can see them here. Now what we want to do is we want to also include the free field elements to be fixed at the bottom. So what I can do is directly here in the workspace, just right-click on my boundary condition and go to Edit. And here we see we're fixing the degrees of freedom Z as well, but it's not really necessary for a 2D case. But I'm just going to reselect. Here now I'm selecting 2 additional elements. And we see now visually that this has been also activated. So I'm including the surface springs into the free field into the boundary condition. And then next, or the last thing would be, is to include or add the acceleration function. So we can go here to load, and this is where you can select if it's going to be an X, Y, or Z direction, or you can actually, through scale factor and geometry, you can actually even have them at a diagonal direction if you activate X and Y or whichever analysis you're doing. And this is where you can go to add a function. You can select from our database, which would be here, or you can directly just copy paste a function from an Excel table. In this case, this is a seismic function from Japan, a Japanese earthquake. Just as a reference, you can use whichever you want. And so just to show that you can just copy paste it directly into the time history function. And you can specify the name if you're having more than one. If you just have one seismic function, it doesn't really matter. And you can do other things. You can select if it's just normalized acceleration, if it's displacement of force, etc. So from here, this is the same one that I just created. So for the start file, it will also be included, just in case you want to use the one we have. We'll also include this Excel sheet in the starting files for people who are going to try the tutorial. But you don't have to copy paste it. The step is already done for you. So you would just have to select from the menu which one you want to use in case you have more than one. We will select the Hachino in the X direction. And then specify if it's a seismic function or if we want to create a new seismic function. So here it's telling me that's already created. As I mentioned, the start file, we left the load, the dynamic load included. But if you wanted to make a new one just to show you, you would just select and give it a different name. And you would be able then here in the work tree to see the 2 different functions. Although in this case, they happen to be the same. So I'm just going to delete this new extra one we created just as a part of the example. So now we'll be at the last part, which is to set up the analysis case for the time history. What we're going to do is we're actually going to do it as a construction stage process. And the initial stage is going to be just the stress analysis, and the second stage will be the time history analysis. So here I'm selecting construction stage set. And we see that we can run different kinds of analysis for construction stages, including semi-coupled, which would be like stress, seepage, slope, other like consolidation, as well as fully coupled stress seepage analysis. And the last option, which is the one we want, would be a coupled analysis for stress and then the nonlinear time history, basically the seismic or dynamic analysis. So we go to Add after selecting. And to turn these commands on, we have to select it from the table. So once we selected it from the table, we'll go on to define it. So this is what the window looks like for construction stages in MIDAS. Since we have a type of analysis that has 2 different options or 2 different types, this is where you would select which one you want to start with. Our initial stage will just be stress. And so here we would just tell it like this is the initial stress stage, and we're gonna drag and drop from left to right everything except the ground surface springs that we used for the eigenvalue analysis. So we would activate even the boundary condition and the free field. Even though this is a dynamic boundary condition, it's also we're gonna also use it for the initial stress analysis and use self-weight as the initial stress. What we're also going to do is we're going to clear the displacements. We only want to see the results based on what's going to happen dynamically. We're going to activate the water level to the same level as we did for the eigenvalue analysis, which is a value of 2. And we're going to save the stage and then create a new one. So once it's saved, we'll go to new, and now we're at the second stage. And then this one will be our liquefaction stage or our seismic stage. And we change it to stage type nonlinear time history. For this one, all I'm going to do is drag and drop to activate the load, the seismic dynamic load. We notice that now, in terms of options, I can only use dynamic loads, not static anymore. Also, you notice that we have new options here. What we see now is that we have to define the time step. So the time step, you want it to match the duration of your seismic function. In this case, it's 15 seconds. And also the time increment in your seismic function. So if I was to show you the Excel table again, we'll see that it's every 0.062 seconds we have a step. So I'm just matching this value here. And then the last option, the intermediate option, is more of a space saving, memory saving option. So that it's not going to help run it any faster. But what it would do is it would create a file. Instead of saving every result, you could tell it to, let's say, make a file half as big by telling it to save every other result. So every 2 outputs, save it in the result. In this case, we're running a 2D analysis, so it's not that important in terms of how big the file is going to be, the output file is going to be. So we can leave it at 1. So I'll just go here to add. And it's going to show us the number of steps, so that's okay. Then the other thing we want to do, I don't need to define the water level again. It's already been turned on in the previous stage. But what I do need to do is go here to the analysis control and specify a few things. In the general tab, I want to tell the program that this analysis, this stage, is going to have undrained material behavior. And then for the dynamic tab, this is where we define the damping method. As I mentioned, it's the Rayleigh. So we will specify our 2 main modes that we calculated from the eigenvalue analysis. And as I mentioned, we will just specify the period for both. And we'll use a damping ratio of 5%. And we just save it. So that's basically it. And we would just be able to now run the construction stage analysis. We would go to Analysis, General, and we tell it here that we want to run a construction stage analysis. We do have other options just to run a straight nonlinear time history analysis or couple analysis for what would be seismic with slope stability. There's different options. We'll run the construction stage. And then in analysis control, we can specify to consider the water pressure automatically, to initialize the stress in the stage 1, and consider other things like the K-naught condition and to cut off negative pressure. So the benefit of doing this by construction stages is that we have more control in the initial stresses at stage 1, including, if you're going to apply some sort of static load initial condition that is going to be considered, then it's best, or we recommend that you do it by stages. If you don't need to consider that, then you can just run a straight time history analysis. Other thing you can also control is if you want to include other results by default, the velocity and acceleration results are turned off, as well as the element strains. So you can just go to output control and directly activate these and then you would just run the analysis, perform it. In this case, only the second one. And it would start running. So in an effort to save a little time, we can just open a model that's finished. Here we're just going through the steps that I just covered, including this crucial one. And so you just run it. And so we can inspect some of the results here. This is the model after it's finished running. What you will see is on the worktree, you have all the, we had done the eigenvalue part before, but now here we have the two stages, the initial and then the seismic stage, and each of these is a time increment for the seismic function or the seismic analysis. And you see that when you expand them, you have results for displacements, accelerations, the beam element forces for the piles, and then the plane, the forces or stresses, including a special for UBC SAND result. So we can go all the way down to find our min, max, and absolute max. So we can look at some results, for instance, relative displacement. We want to take the, keep the actual deformation, or if we want to exaggerate it, we can control that. Deformed or undeformed. Vector diagrams. What we could do is also probe, select specific points directly on the model and look at results. We can change the units after running the analysis. So now we're looking at millimeters. So these are their max relative displacements. And what that means is that the base nodes are 0. It's basically relative to the bottom of the model. So this is the correction basically for it, which is different than total displacement, which shows the whole thing moving kind of thing. So what we also want to see are the accelerations, relative accelerations. We see here we have, I'm going to change the units back to meter per second square. So at the base it's 0, and we're seeing amplification and acceleration increase of up to 3.2 meters per second squared near the, I guess, near where the abutment is, or right behind the abutment. We can extract these results to see them graphically. I'm going to take the vectors off. We have this function called extract. And from here, we would first have to be careful to select which analysis set we want, which will be the second one. And then from here, we would just select which results we want to, which result type we want to extract. So let's do relative accelerations. Here are all the time steps in the results. So what you can do is you can ask for the maximums or the minimums, or you can just specify points of interest. So let's specify that point where the max is. Let's specify a point. Maybe it can just be at the top of or on the abutment, and then let's pick one final point near or on the base. So we have 3 sets, and we just go to table. And from here, we can graph all 3 directly, or we can export it to Excel. So this would be our results. We can also do the same if we wanted to be more specific, let's say only in the X direction. And even if you change it, the nodes stay selected. So I can create a new graph for accelerations in the X direction, which is in the direction of the seismic function. So here we see the blue node being at the base, and then these 2 nodes at the different behind and on top of the bridge abutment. So it would be, for instance, for accelerations, but you can do the same for any kind of result. For instance, if we wanted to look at the increase in port pressure. So for that, we would go here to the results for plane strain stresses. We can expand this here. And we can look at excess port stress. So this is at the maximum values, but we can also graph this in a similar procedure. Select the case, plane strain stresses, excess pore stress. And let's just say we care about the maximums. We don't necessarily have a particular point. We just want to see what the maximum value of that would be. So you can easily graph that over the process of the analysis as well. So we see here, we see an increase and then a stabilizes at the end. And then other important results would be, for instance, the beam element forces, so axial forces on the beams, or the moments on the beam, on the piles. And then the last important result would be the one for liquefaction, which would be here the UBC SAND results. So these are the two results we have is the pore pressure ratio. So it's the difference in pore pressure over in the initial pore pressure. And then the other one would be the normalized max stress ratio. So we're looking at the mobilized friction angle over the peak friction angle. And basically, if this ratio gets close to 1 or higher than 1, then we identify that as the soil becoming liquefied, or it's basically liquefaction is triggered when this value becomes 1. So in this case, we're looking at the red region and some of the yellow region as the area identified as the region for where liquefaction has occurred. And if we were to use this bar menu down here, we can go through the different stages to even identify at what stage in the seismic function this happened. I can use my keyboard to go left and right in the time, if you will. So here we see the jump from 0.76 to 1.1. So about 4 seconds in is where we're starting to see this liquefaction effect occur. So that would be the, I guess, recap of the results. This is a very handy tool, the extract function, for these kind of seismic analysis where you need to graph what's happening. And these are the special results that we have for this liquefaction analysis. So that would be the conclusion of our step-by-step training.